Oh, that wasn't recording?
Okay, so hydrogen bonding, again, is a little bit different than the other types of bonds that we talked about, covalent and ionic, because it's not a bond within a molecule, it is a bond between two molecules that are next to each other. Okay, and again, this is going to come up later in the year, and it's usually shown as a dotted line, and so it's two molecules that are attracted to each other, they're kind of cozied up together, and that's called a hydrogen bond. That is why our water was so sticky and held so many drops on that penny. Okay, it's because those water molecules are hydrogen bonding to each other. But water is not the only substance that we see doing hydrogen bonding, but it is the big one. So, when water is doing hydrogen bonding, it is an example of cohesion. Cohesion means that there's an attraction between molecules that are the same. So molecules of the same substance attracted to each other. Okay, we notice this again in our lab with the water molecules. But it can be anything that's the same. It doesn't have to be water molecules, but we see this with water. Similar to cohesion, but a little bit different, is adhesion. And maybe you haven't noticed this, the example that it gives you, but maybe you did notice it. Adhesion is when there's two molecules that are different that are attracted to each other. So for example, when you pour water in a graduated cylinder and you are taking the measurement, if you look very carefully, the water is creeping up the sides of the graduated cylinder. It makes a little curve. Curve is called a meniscus. And that's because that the water molecules are attracted to the plastic side of the graduated cylinder. It's even more obvious when you use a glass graduated cylinder, but it's because the glass molecules and the water are attracted to each other. And again, adhesion's that's not the only place we see it, but that's just one example of molecules that are different that are attracted to each other. Okay, the last part of this section, that's not true. The next part of this section is about solutions. Okay, we are going to definitely be looking at atoms and molecules, but sometimes we're even going to get bigger than that or broader than that, and we are going to look at compounds that are mixed together. Okay, so a lot of times when we see these mixtures, water is going to be one of the substances or compounds in the mixture. So a mixture just means something that is two or more things, can be elements or compounds, two or more things that are physically mixed together. Let's talk about what that means. Okay, physically mixed together means that they are put next to each other and mixed, but they are not chemically combined. This is something we really clarify in chemistry, but chemically combined means they have made a new compound. A mixture is not that. It is just exactly what it sounds like. They're mixed together. Okay, and we see this a lot in our living things, so that's why we need to clarify all of this vocabulary. So a mixture is two or more two or more things that are physically mixed together. My chemistry class loves the example of fruit salad. Okay, so fruit salad, we've got more than one different type of fruit physically mixed together. You could still separate all the strawberries from the bananas and from the grapes because you only like grapes. Okay? Now, most of the time, these mixtures are so thoroughly mixed, not like a fruit salad, they're so thoroughly mixed that we call them a solution. Now, don't worry here that it says ions. I wouldn't worry about that. Let's use the example of lemonade. Okay? If I'm making lemonade, I've got lemonade powder and water. When I mix that lemonade powder in there, eventually, if I keep mixing, it is going to be all the way distributed or evenly dispersed. When that happens, I'm going to call that a solution. And a lot of times in biology, we are going to be looking at solutions. That means something has been all the way distributed. Usually we're talking about in water. Not always, but most of the time. Okay, so solution is basically a mixture that's all the way dispersed, evenly dispersed throughout. Usually we're talking about water. Okay? So all the components are evenly distributed. That basically means for every sip of lemonade I take, it's going to be the same sip, the same stuff. And each thing in there has a name. What we dissolve is called the solute. So what is dissolved is called the solute. So in my lemonade example, it would be the lemonade powder. Okay? So whatever is being dissolved is called the solute. Whatever is doing the dissolving is called the solvent. Almost always, the solvent is water. Water is often called the universal solvent. Okay, so this is giving a couple other examples. Salt water. In salt water, salt is the solvent, and salt is the solute, excuse me, and water is the solvent. Okay, what about sweet tea from McDonald's? There's actually more than one solute. What's the solutes?
Tea.
Sugar. And sugar. Plenty of it. That's exactly right.
Depends on which type of tea.
And
because
then
they
solvent.
have unsweet.
True. They do have unsweet. And then the solvent is?
Water.
Water. Good. Then the bottom talks about, this isn't on your note outline, but it says when a given amount of water has dissolved all the solute it can, the solution is said to be saturated. I think McDonald's sweet tea is a saturated solution. Sometimes there's a layer of sugar on the bottom because it cannot be mixed in anymore because the water is holding all of the sugar that it can. The water has dissolved all of the sugar that it can. Okay? It's not a big deal, but sometimes we'll see this in living things. Sometimes there's the maximum amount of solute has already been dissolved and the solution or the solvent can't hold any more.
Is that why they sweat?
Not exactly.
Dylan's over here shaking his head like,
We'll
I
get to
should have
that.
known that.
We'll get to that. Okay, now we're at the last part of this section. Okay, the last part of this section, and this does feel awkward for me to, in the same breath as talking about McDonald's sweet tea, to talk about pH, but that's because this chapter is basically laying the groundwork for terms that we are going to use the rest of the year. So, it is a weird transition for me too, but we're just going to deal. Okay? The last little bit of this is going to talk about acids and bases and pH. And we are going to do a lab tomorrow about pH. And this is something that's going to stick with us the rest of the year. It's going to kind of pop up, come and go. And so it's important that we understand what pH means. Okay? That's all fluff. Okay. So when water splits apart, here is the reaction. Here's what it looks like. This is what actually happens. So we know water is H2O. Okay, 1 oxygen and 2 hydrogens. And when water splits in half, the oxygen doesn't split in half, but when water splits in half, there's OH that are still stuck together, and then a hydrogen that's by itself. Okay, and those have fancy names. The hydrogen is called a hydrogen ion, and the OH is called a hydroxide ion. Basically, I want you to think about this as water splitting. Okay? It just doesn't split equally, but it does split into 2 pieces. That makes sense. Okay? And so we're going to see that sometimes water is going to break apart. And when water breaks apart, we are able to measure how much of the water is broken apart. Now you're thinking, why is this important? We're going to understand why it's important here in a little bit. But anytime we see a reaction like this, just to recap, here is the reactants. This is what we start with. And then you see an arrow. We'll talk about why that has a double arrow. And then this is the product. That is what is created or what the end of the reaction is. Usually you just see an arrow going to the right. This one means that this reaction is reversible. Okay, this reaction water can break apart, and then these 2 pieces can bond back together and make water. Okay, so it is going in both ways. Okay, so how does this relate to pH? So in pH, what we are measuring is the amount of water that has split apart. Okay? And how we measure that is we measure the hydrogen ions. Seems easy enough, right? So we are measuring the hydrogen ions when we measure pH. And again, we'll get to what different numbers mean here in just a minute. But when water splits apart, you would expect these 2 pieces to be the same amount. So for example, when I have 1 water molecule that is going to split, I would expect 1 hydrogen and 1 hydroxide. Okay? when another molecule of water splits apart, I would expect one hydrogen and one hydroxide. That's what I would expect. I've got one molecule, and when it splits into two pieces, I have one of each piece. Okay? But that doesn't always happen. Okay? Sometimes the water doesn't always dissolve in that way, and other times when it breaks apart, the hydroxide ions go bond with something else, or the hydrogen ions go bond with something else. And sometimes water is mixed with other things that also have hydrogen ions and hydroxide ions. There's lots of reasons that there wouldn't be an equal number of hydrogen ions and hydroxide ions. So the pH scale measures how many hydrogen ions are in the solution. That's what concentration means. How many hydrogen ions are in the solution? The concentration of hydrogen ions, and you can write it as an H+. So for pure water, perfectly pure water, you would expect the number of hydrogen ions to equal the number of hydroxide ions. And when that happens, the pH level or pH number is 7. So when those ions equal each other, the pH is 7.
Are we going to do a live on this?
We are going to do a lab on this tomorrow.
Sweet.
Okay, but again, depending on what water is mixed with, you can expect that that's not always the case. Okay, so sometimes there's going to be more hydrogen ions, sometimes there's going to be more hydroxide ions, and the pH scale is measuring all of that. Okay, so anything below a 7 is considered acidic, and that's because it has more hydrogen ions than hydroxide ions. So anything below a 7 is considered acidic. It has more hydrogen ions than hydroxide. And the lower you go, the more hydrogen ions you have. Okay, so if I have a pH of 2, that is more hydrogen ions than a pH of 4. But again, it's still measuring the number of hydrogen ions. Okay, then the other side of the scale goes from 0 to 14. The other side of the scale, substances that have a pH higher than 7, is because they have more hydroxide ions, or that OH. And so if they have more hydroxide ions, that means they have less hydrogen, and that solution is considered basic. Basic is the opposite of acidic. The other thing I want to point out about the pH scale is that each step on the pH scale is a factor of 10. Okay, so consider it as an exponent of 10, times 10 or divided by 10. So for example, if I was looking at something that's acidic at a pH of 6, that has 10 times more hydrogen ions than pure water at the pH of 7. Okay, so it's a factor of 10, 10 times more hydrogen ions. Then if I were to go to a pH of 5, it's 10 times more from the pH of 6. So that is how the scale works. And you are probably familiar with some of the solutions on this scale as being acidic. You probably know that lemon juice or citrus juices are acidic. And then maybe the basic stuff, maybe you didn't know, but most cleaning products that we use are basic. And then things that are mostly water are going to fall really close to that 7 mark. So it talks about, I can't even see that. Acid rain is mostly water. Human blood is mostly water. So those are going to be pretty close to 7.
And milk. I'm surprised milk is on the acid side. Like it's